third talk of Balázs mini course, so thank you.
Okay, thank you very much. And today I would like to continue with the generalized projection scheme, which is a kind of bunch of conditions which try to cover as large family of projections as possible, which are possible to be handled by this transversality method. So the first versions was introduced by Boris Solomiak, but now I would like to give you some more seemingly more general version, which we believe that covers a larger system of possible transversal systems. And this is what we also used in our paper with Károly Simon and Adam Spiewak. So I will present you a bunch of abstract conditions now, because we need a phase space. And what I claim is that let this X be a phase space, be a compact topological space. Okay? This will be from where we would like to project. Then let U be a separable metric space equipped with a locally finite Borel measure, let's say eta. This U will play the role of the set of parameters. Okay, so what do we want now? We want a family of projections, right? So first let pi of lambda be a family of projections from X to Rd. B maps, and I don't tell anything at the moment. What are the properties? B maps for all possible parameter value. But what I want is also to provide good and almost optimal smoothness properties for this projection. So in order to do so, I also would like to introduce a set D lambda be a family of metrics on my phase space X, generating the given topology. Why do I do that? Why do I have this bunch of metrics instead of fixing one metric? Recall that in the case of iterated function systems, so this is just a side note, but recall it was easier to work in the case of IFSs when I had this parameterized map. Right? The natural metric for one given IFS on the symbolic space was the subnorm of the derivative of the compositions. So if my maps depends on a parameter, then my metric will depend also on this parameter. Okay, so this is why I have now a big family of metrics. Of course, not any kind of family of metrics will be good, because we require a few natural things. The first thing what we require that these maps, pi lambda, shall behave like orthogonal projections, which means that I claim that they are Lipschitz with respect to these metrics. Okay? So what I claim is that for every lambda, you can find some constant such that if you are looking at the distance of two elements, p lambda x, p lambda y, this is at most c lambda of the distance with respect to lambda of x and y. And I don't claim that this constant is uniform everywhere. Okay, what else? I also want that these metrics not only generates the same topology, but they are also transforming in some continuous way. Namely, what I claim is the following, that whatever point you are at for every lambda naught, and for every psi in 0, 1, you can find some neighborhood of lambda naught in such a way that if you're looking at the distance of 2 points of lambda naught, you can also find a constant, this should be also a universal constant, such that whatever points you look at, these distances will be more or less equivalent with the lambda distances. This is supposed to be minus, and this supposed to be plus. Okay, so I expect some continuous change of the metric, and this should be true for every x and y from my phase space. Okay, so every metric, of course, constructs for me its own Hausdorff measure and its own Hausdorff dimension, but this condition B also implies that the Hausdorff dimension changes in a continuous way. Okay, so Hausdorff dimension changes continuously. Okay, and so these are my continuity properties, what I expect from my maps and my metric, and what I also expect is the transversality condition. So what shall be the transversality in this regime? And we make things flexible just in order to be more relaxed. And let's say the following: for every lambda naught and for every epsilon, I can find again an open set, and I can find also a constant such that whenever I'm looking at the set of parameters from this little neighborhood of lambda, where what I see is that the images of x and y are too close to each other. Well, I already know that this is Lipschitz, right? So what do I mean that they are too close to each other? They are supposed to be at least at most that close times some constant, right? But I want to take here some small r number. So they are much closer on RD than they are supposed to be on my phase space. Okay, and also, which one? Oh, Roland, oh yeah, sorry, my bad. I should have kept the same notation in my notes and on the blackboard. Yes, it's d lambda, that's the metric. Yes, thank you. Sorry. But I also can relax my condition that the distance of x and y is at least some delta. This should be at most k times delta to the power minus epsilon r to the power d, and this should hold for every small r, every small delta, and every x and y. So what does this mean? This means that unlike in the previous cases, my constant might blow up. So I give some sub-exponential speed with respect to the distance that my constant can blow up to cover more things. Also, this is the condition which says that although I know my orthogonal, my projection is Lipschitz, but if the images are too close to each other with an R, this should be comparable with the measure of a ball in R to the power D, right? Because we are now projecting to RD. If we would project on the line, then this would be just simply R. Okay, so these are the what I call as generalized projection scheme, or GPS for short. Okay, and if you have these conditions, then you can reproduce basically all the previously known results in the iterated function systems. But also there are many relaxations here to cover much more. For example, this GPS co-covers, of course, orthogonal projections. It also covers a family of nonlinear projections. With certain properties. But also it covers not only the iterated function system business, but also the non-autonomous iterated function systems. What are the non-autonomous iterated function systems? Instead of having one IFS who is parametrized, right, and depends on some parameter lambda, I have a family of iterated function systems where everything index set, everything can depend on n. And what you consider is the following orthogonal projection from the phase space, which is just the usual product of these symbols. Pi of lambda I equals to the limit, n goes to infinity. Of course, you need to assume some kind of contracting, uniform contraction property and things like that. I don't go into the details, just I would like to show that it's also possible to be applied for some kind of overlapping Moran type constructions. Okay, so this one, and this is Fi11 composed with Fin, and if you set up everything in a uniformly contracting way, then again I can choose this point whatever I want. And such kind of systems, the transversality method was introduced very recently by Nakajima for these non-autonomous systems. And basically he was also studying the example that you can say the distribution of the following modified Erdős problem, where instead of having plus minus, right? Because in this way, if you choose the plus and minus as an IID random variables with being plus probability 1/2 and being minus probability 1/2, it's a classic Erdős problem. And he considered the case when you add this extra shrinking sequence 1/n. And he also verified regions for absolute continuity and dimension for almost every lambda. Okay, but also in some sense, it also covers the business of random iterated function systems. What do I mean by random iterated function systems? So in a case of an IFS, you fix some IFS, Fi, and for every finite word, you try to keep the iteration, but you always add some kind of random noise. Okay, what you consider is a family of random variables, Ti, who are, let's say, for simplicity, independent, identically distributed with bounded absolutely with bounded, no, okay. IID random variables who are absolutely continuous with bounded density. Bounded, absolutely continuous, let's say also compactly supported. Right, because you imagine the random noise to come from some tiny interval. But this is just for the simplicity. There are more general cases for that. And what is my IFS? Well, basically, in each iterate, I add the random noise, right? So here, I apply the function fi1, and I add the random noise corresponding to I1. Then I apply my function I2, but I add the random noise corresponding to the finite word I1, I2. And so on and so on. You continue it, In plus Ti1, Tin. And this is your random natural projection. Okay, and such kind of systems, I mean, in the case of simply random iterated function systems, it has a long history going back to Maudin, Williams, Falconer. Lots of people were studying these random constructions. In their cases, there were no overlaps, but in the overlapping systems were studied by Jordan, Policott, and Shimon. Also, Koivusalo was studying it, 14, let's say, and we with Antti, Keinmäki, and also Michal Rams consider these overlapping random iterated function systems quite recently. But in the case of random iterated function systems, I'm lying to you a little bit. Because your metric will be a random metric, right? For every, who are the parameters? Your parameter space is this big set. And my metric will be a random metric depending on all of these random variables. And you don't really have this continuity property B in the random IFS case. However, there are certain ways how to handle these difficulties. Basically, what you really need is not this one, but the continuity of the Hausdorff dimension, which you have, because actually the Hausdorff dimension will be not continuous, will be constant almost surely, because it only depends on the tail events. So the Hausdorff dimension stuff will only depends on the tail behavior, which is, well, a constant behavior. Okay, so you can get rid with that things. Okay, but, and also there is one thing which is, yes please.
The IFS case, do you need some kind of separation condition to put it in this framework? Or?
No, exactly. The point is that it provides you that you can handle the overlapping situation. So the whole point is to handle the overlaps in order that you find some well-behaving parameterized family. And for that well-behaving family, you can say that, okay, almost surely I know my dimension won't drop, or I will be absolutely continuous. Okay? Yeah, but it doesn't cover. This frameworks is the non-conformal setup. It requires different type of transversality condition. Because imagine why. We know that this system of projections is Lipschitz. But what if it's not conformal? Namely, there are some directions where this Lipschitz property would really taking much stronger contractions. And although it's Lipschitz, on these directions, you really expect that these points along the strong stable foliations, strong stable fields and directions, we expect that these points are really much stronger to each other than they are supposed to be symbolically. And that's why this is not the correct bound for that, but this bound works very well if what you expect is conformal. your change, your contractions are the same in every direction. Okay? Yeah, so this is the GPS system I want to tell you. And now, yeah, are there maybe further questions? No, okay. So let us make a detour. Because, of course, one could say that now the natural thing to state is that grab a nice mu measure, then for almost every parameters, its projection won't have dimension drop, almost surely. But I want to show you something more sophisticated, and now I would like to show you what is the motivation behind that. Because I not only want that I grab a measure, I project it down, and I know that for almost surely there is no drop. Because a priori, this zero-dimensional set of exceptions, where the dimension might drop, depends on the object, might depend on the measure I'm projecting. And what I want is something universal, which is good for everything. So let me tell you what is the motivation, because it might be a little bit mysterious at the moment. So there is this very nice results by Mike Hochman, Ariel Rapaport, and Pablo Schmerkin. Right? So now we make some detour for further motivations. Right? Hochman considered self-similar iterated function systems on the real line and said the following: if this phi satisfies the exponential separation, in short ESC, then for every Bernoulli measure, for every mu Bernoulli measure, on my symbolic shift space, if you project it down to the real line, and this pi is my natural projection, its dimension does not drop. Its dimension is minimum of 1 and entropy over Lyapunov exponent. So what you need is that, can you verify the exponent? I don't tell you at the moment what is the exponential separation condition, and I will tell you in a minute. But if you can verify this, then you know that simultaneously for every Bernoulli measure, the dimension value, what you expect from symbolically, won't drop. Also, he showed that this is a typical property, namely, if you parameterize, I should not have used this as a contracting ratio, let R be the contracting ratio, then I can freely use the parameters as lambda. So he also showed that if you choose the parameterization of the contracting ratios and the translation parameters, who are the natural parameters, in an analytically and in a non-degenerate way. What is the non-degenerate way? Well, basically, if you take two different words from the symbolic space, what you want is that they are not uniformly the same for every one-dimensional parameter value. Okay? So they differ somewhere. Okay? On an interval U. And then what he showed is that on this interval, the exceptional set where the exponential separation does not hold. So you can find any, let's say, a priori, you can find any Bernoulli measure where the dimension drops. It has a 0 dimension. Right? So he showed that the dimension of lambdas where no exponential separation has dimension 0. So there is a big pile, a big set of parameters where you have simultaneous dimension result for every Bernoulli measure. Furthermore, that was generalized further by Jordan and, oh, it's here. It was generalized further by Jordan and Rappaport. Who were saying that you have this no dimension drop simultaneously for every ergodic measure. So if you have exponential separation for this self-similar system, for this IFS consisting only on similarities, then simultaneously for every mu ergodic left shift invariant on sigma, the dimension won't drop. Okay? And this is exactly our motivation. That is it true also in some more general case that you, not a priori, you can say something stronger, that my parameters should not depend on the object, right? What I'm projecting. Why? How my mu measure comes into the business and says that, okay, but I don't like this and this and these parameters. Of course, in big generality, you cannot expect such kind of simultaneous result. Okay, for example, so our goal is now this simultaneous projection results. Try to find some kind of condition. Yes, please?
So in general assessment of any ergodic simulation,
Yes.
so you don't have that result about the exceptional set?
No, it's the same. So what they require is the exponential separation condition. So over the points where the exponential separation holds, you have this. And these are typical. So then where the exponential separation condition fails is a 0-dimensional set. And exactly if you choose these as parameters, then, okay, just for simplicity, for Lebesgue, almost every choice of contractions and translations, you will have almost surely exponential separation. Yes, so they only required this to know whether there is exponential separation. So whenever you know that you are out of this bad exceptional set, then you are fine, and you can project whatever you want. I mean, of course, ergodic measures. Oh, yes, no. No, unfortunately, it's not known at the moment. So there are results due to Pablo Schmerkin, Saglietti, Solomiak, where they provide very good estimates for self-similar measures where you know absolute continuity for Bernoulli measures. I'm not aware of that it's generalized already for ergodic measures. And also, you require something much stronger than the exponential separation. You also need to know that the Fourier transforms have some sufficient decay. But also, you need to rely on Pablo Schmerkin's works on LQ dimension. But I'm not aware that absolute continuity is done in that generality. for ergodic measures, but for Bernoulli measures, yes, Saglietti, Solomiak, Schmerkin.
When mu is the Bernoulli,
Yes?
then the push forward under the natural projection is the invariant measure of
Yes,
the stationary measure.
exactly, exactly. When it's the natural measure, then he is the only guy who satisfies this equation. How should I write? Fi. Oh, too many stars. Yes, so it is the only, this is the stationary one.
And
Exactly.
when it's not Bernoulli, do you have some kind of interpretation like that also?
There are some. So for example, if you are considering, so not in the full generality, not for every ergodic measure, but for example, if you say the following, I'm on the interval 0, 1, I should be down. I'm on the interval 0, 1, and I define some functions, P1 of x, let's say some other P2 of x, in such a way that for every x, they sum up to 1. Okay? And whenever I am in a certain point x, then I will jump. So it's also the stationarity, and it's also a Markov process, but the probability that now I will choose the ith function and jump to fi of x depends on pi I. So if you wish, this measure then, let me write by nu, can be written as pi I of x, okay, for some observable phi fi of x. And such kind of guys, if these probability measures are smooth enough, are essentially Gibbs measures on the symbolic space. Okay, but you can also study them with these methods. I don't know any better representation for it. Okay. Yes. So now our goal is to achieve some simultaneous property also in the framework of GPS. And what I wanted to say is that in full generality, of course, you cannot expect this. For example, let us go back to the case of Marstrand's projection. Oopsie. Sorry. So let us go back to the case of Marstrand's theorem, the simple orthogonal projection. Right? Or a theorem of Hu and Taylor. So they said that grab a measure mu, have this p theta orthogonal projection to the line with slope theta, and then you know that for almost every theta, this projection has no dimension drop. So its dimension, my proper meaning, lower or upper dimension, is what it should be. But consider simply a family. Let mu be the Lebesgue measure on the 0, 1 interval. And let us consider R to be rotations. Okay? And I consider the whole family. I rotate my mu measure. Of course, I cannot expect that Marstrand's theorem holds simultaneously for all of these measures, right? Because whatever direction I pick, whatever theta slope I pick, let's say this is the theta slope I picked, from this rotated family, there will be a guy who will be just perpendicular to this line, and my projection will be just a Dirac mass on the origin. And this is a heavy dimension drop. So I need some condition on the measures which I'm projecting in order to expect that simultaneously for all of them the dimension won't drop almost surely. So what are these properties? We have this big topological space which is metrizable, and we actually have a huge family of metrics. Matrix, yes. So let Px be the Borel probability measures on my compact topological phase space X. And what I'm saying is, I need to find what I'm saying because I'm lost in my notes. Oh, yes. So if you choose a measure, then it is almost doubling if you are looking at the tiny ball around X divided by a tiny ball with radius 2r. Okay, so it's a metrizable space. We have a bunch of metrics, right? So these balls make sense, and these balls I want in every metric to hold the following. Okay, so it would be doubling if I would know that the measure of this guy is bounded by some uniform constant of that guy. But I'm very happy that if I'm looking at the exponential error of this constant related to r, that this has zero, it does not grow exponentially for almost every x. Okay? So I don't need doubling, but I need some regularity. Okay. For two measures, let's say mu and eta, define the relative entropy dimension as follows. So the dimension of the measure mu relative to nu should be the maximum of the essential supremum regarding mu of the lim sup of log of the mu ball xr divided by the ball with respect to nu divided by log r, and also the essential supremum of the lim sup of the same stuff, but it's flipped. So the new measure of the ball bxr divided by the mu measure of the ball divided by log r. Okay, so this is what we consider the relative entropy dimension. And it can be infinite, right? Because observe that very simply, if I choose a measure which gives positive mass out of the support of nu, then for those values, this nu measure of the ball is 0. Then this guy blows up to infinity. So it might be very much not finite. But it represents somehow that how the dimension changes from one measure to another. Namely, can I reach one measure to another continuously? Whatever it means. But at least, on one sense, this heuristic can be made precise. Namely, we say that a collection of measures is regular dimension separable if I need that every measure needs to be that regular at least. If every mu from my collection is almost doubling. And secondly, I can find a countable subset of M in such a way that for every epsilon and every mu measure from my collection, I can find an eta element from this countable collection that the relative entropy dimension of mu with respect to nu is smaller than epsilon. In a way, feel free to think about this problem as follows. I'm interested in those set of measures, those collection of measures, which are forming a separable, this is not in marks, but metric space with respect to the Kullback-Leibler distance. This is somehow the background idea. Okay, and this is our theorem which says, which is due to myself, Károly Simon, and Adam Spiewak, and we showed that if you have this GPS system and you have this collection of measures who is regular dimension separable, you should also abbreviate this. Regular dimension separable. Then, for almost every choice of parameters, the upper and lower Hausdorff dimension of the projection of my measure does not drop. Namely, it is equals to the upper and lower Hausdorff dimension, where this Hausdorff dimension depends on lambda, because remember, my parameter space for certain lambda values associates a metric who depends on lambda. So my Hausdorff dimension here also depends on lambda for mu. But what's the point is that my exceptional set does not depend on my measure, and it holds for every measure mu. And okay, you might say that that's very nice, very abstract. What is it good for? Because if it's good for nothing, then I wasted your last 3 times 45 minutes. And I hope that you won't find that I was wasting your time, because let me show that there is a very natural family of measures which satisfies this. So, theorem, let's consider the shift space with a metric which has the following form. So this is a function who depends only on the joint part of I and j, their common part, but in such a way that for every word I can find a universal gamma value which is smaller than 1, that if I'm looking at what is the phi function at this finite word, it shrinks down exponentially if I decrease the order. And basically, most of the measures on the symbolic space, the shift space, satisfies this property. Then, ergodic sigma invariant measures ergodic sigma invariant measures are regular dimension separable with respect to this metric D. Okay, so this is basically a huge pile of natural measures satisfying this condition. And in particular, you can say the following. For an IFS, so just to summarize what we have seen so far, for an IFS Fi of C1 plus alpha contractions such that you choose the sum of the contracting ratios to be strictly smaller than 1. For Lebesgue, almost every translation parameters and for every mu ergodic, if I project down my ergodic measure to the real line, yes, it's on the real line, then it does not drop simultaneously. Okay, this is a system where we have seen that satisfies the transversality and the GPS, this already, and the ergodic measures, what we have seen, that satisfies this relative dimension separability. Okay, and tomorrow on the next lecture, I will show you how to apply these things for multifractal analysis. So thank you very much.